In this recording, we'll discuss electrophysiology. As we've learned, all neurons are excitable in the presence of stimulus. And these stimuli can be electrical changes across the neuron's plasma membrane. Okay, we usually call that an action potential. And these will then be rapidly conducted along the entire length of the membrane. Okay, so if you think back to the neuromuscular junction that we have discussed, we took an action potential from a neuron, the axon terminal, and we transferred it over to the sarcolemma. And the sarcolemma, we then took the action potential and propagated it across the entire sarcolemma. Okay. It's the same idea here. Now we are just working with transmitting an action potential from one neuron to another neuron. Okay. We have two types of electrical changes. We have local potentials, and then we have action potentials. Action potentials we are super familiar with by now. These travel along the length of the entire axon. Local potentials are just a little bit different. These only travel very short distances, but these are similar to the end plate potentials that we discussed in muscle physiology. So again, if you remember back to the neuromuscular junction, taking an action potential from an axon terminal, sending it over to the motor end plate, we created those end plate potentials. We talked about if we had enough end plate potentials, we could trigger an actual action potential. Okay, so local potentials, end plate potentials, basically the same thing. Okay, we're just dealing with two neurons now instead of one neuron and a muscle. We have additional channels that we are going to use throughout the nervous system that we didn't necessarily mention in the muscle physiology system. We have previously mentioned ligand-gated channels. Last time we talked about ligand-gated channels, the ligand that we mentioned was acetylcholine. Okay, when acetylcholine bound to the ligand-gated sodium channels on the motor end plate, it created those end plate potentials that could trigger an action potential. So you are already familiar with ligand-gated channels. You know that the ligand or the specific chemical has to bind to the receptor in order to open these channels. Okay, so those we're familiar with. Leak channels, well, they're always open. You can see in our picture there is really no gate to close, even if we wanted to. The ions will continue to flow down their concentration gradient between the cytosol and the extracellular fluid. They just kind of go back and forth depending on where the higher concentration gradient is. So if we start with a high concentration gradient outside the cell, they'll flow inside the cell. If we build up our high concentration inside the cell, then the ions will flow outside of the cell. Voltage-gated channels we're also familiar with. You know that these open and close in response to changes in voltage across the membrane. So we have talked about voltage-gated sodium channels being activated, inactivated, and being at rest. So you already know that if we change this membrane potential, this can cause our channel to open. Okay, and if this membrane potential goes back to rest, then this gate would close and ions would no longer be able to pass through. Now, our last type of channel, again, is pretty new to us, mechanically gated channels. These open or close in response to mechanical stimulation, which could include pressure, stretch, or vibration. Okay, so you can see in a little picture, we're just touching it, okay, to open the channel. It's kind of like pushing a button. Okay. So, you have become familiar with the idea of membrane potential, specifically resting membrane potential, and then changing membrane potentials during action potentials. That discussion was in regards to muscle physiology. However, neuron physiology basically works the same way. Okay, so at the plasma membrane of the neuron, or the neurolemma, we have a charge difference here. Okay, our resting membrane potential for neurons is approximately -70 millivolts. Okay. Hopefully you remember what our resting membrane potential value was for skeletal muscles. If not, look it up. Okay, I don't want you to get those two numbers confused. Okay. We have mentioned previously the idea of These charges representing electrical potential or potential energy, and you know that we can use that potential energy to transmit signals in the form of action potentials. Okay, so this is fairly familiar to you. All we're really changing is the actual value of resting membrane potential. So now we're at negative 70 millivolts. Okay. Now, just in case you have forgotten, there are factors that help us reach and maintain this negative 70, this resting membrane potential. First of all, we have the sodium-potassium pump. Keep in mind that we are pumping sodiums back out of the cell. We're pumping potassiums back into the cell. We would have to use good old-fashioned ATP to accomplish that. So that's the sodium-potassium pump. Okay, so using the ATP, our favorite energy source, we're going to move sodiums and potassiums against their concentration gradients to assist with reestablishing resting membrane potential. Now, leak channels, and we just kind of introduced ourselves to leak channels, this idea that we have channels that are always open and closed. Potassium will diffuse through these leak channels more easily than sodium. Okay, so you can see we have potassium leak channels, we have sodium leak channels, and the ions move through their respective channels. But potassium, it's just easier for it to move through his channel versus sodium moving through her channel. Okay, but these two guys work together. Okay, these are the two big factors that play a role in the negative resting membrane potential. Okay, maintaining that. Because remember, action potentials, we are going to go away from our resting membrane potential. We're going to jump up positive, but at some point during repolarization, we got to start winding our way back down to this negative 70, and these guys help us do that. Okay, so local potentials. We said that these are small local changes in a neuron's plasma membrane. These serve as triggers for legitimate action potentials. Here's a giant difference that you are going to want to make note of. Circle it, highlight it, star it, something. Make yourself a flashcard. Local potentials, we have two kinds. We have some that do depolarization. We have some that do hyperpolarization. Okay. Now, depolarization, we are experts on. Okay. We start at that resting membrane potential, that negative value. We start moving sodium ions around. We jump to the positive value. Okay. And then we'll eventually come back down during repolarization. But depolarization, we're becoming less negative. Okay. That's familiar. Now, hyperpolarization is not something that we brought up in muscle physiology, so this is brand new. Okay. Hyperpolarization, we have two ways we can do it. We can have positive charges exit the cytosol, or negative charges enter the cytosol. Doesn't matter which way we do it, the end is the same. The membrane potential becomes more negative. Okay, so in depolarization, for example, we went from negative 70 to negative 60. We're becoming more positive. Hyperpolarization would take us from negative 70 down to negative 80. Okay, wrap your minds around that. Wrap your minds around that. That's going to become a big deal here soon. Okay. Sometimes we call these graded potentials because they vary greatly in size. So sometimes you'll only go from negative 70 to negative 60, negative 70 to negative 80, like a very small jump. Sometimes you can have a much bigger jump. So we have a lot of variety here. All right. We have to make sure we are experts on what happens to sodium channels, voltage-gated sodium channels, and voltage-gated potassium channels during action potentials. Okay? Because they're going to be different. So your voltage-gated potassium channels, okay, we're going to start with those. They're a little simpler. Remember, potassium channels are only involved in repolarization, first of all. And second of all, we have two options for voltage-gated potassium channels. You're going to like these guys. Resting state or activated state. That's it. We can be closed or we can be open. Right? Like, that's pretty good, right? Okay. So it will not shock you to learn that in the resting state, the activation gate is closed. You will notice that there is no potassium moving through this channel. Okay. In the activated state, our activation gate has opened up and our little potassium has exited to the extracellular fluid. This is it. These are our only two options, open or closed, activated or at rest. Okay. And I'm making a big deal out of that because sodium channels work differently. Okay. So get familiar with this. Open, closed, activated, at rest. That's how potassium channels work. Now, you'll notice in sodium, we have an extra step. Okay. Sodium has two different gates. We have an inactivation gate and we have an activation gate. Okay. So I think these look like chicken wings and I think this looks like a bathtub plug. Okay. Use whatever examples make you happy. Because we have two different gates, we have three different options. Okay. We could be at rest. Okay. At rest means that our inactivation gate is open, so our bathtub plug is out of the way, but our activation gate is closed, so our chicken wings are blocking the road. You will notice that there is no sodium moving through this channel. Okay. From rest, we move to our activated state. In our activated state, our activation gate is open. Okay. Our inactivation gate is still closed. We have not touched that yet. Okay. And you'll notice that sodium is now free to move through our channel. Okay. Here is our third state, okay, that we did not see with potassium. Between rest and activation, before you can go back to rest, you must inactivate sodium channels. Okay. The activation gate is still open, but the inactivation gate has now closed. Our bathtub plug is plugging up our hole. You will notice there is no more sodium moving through this channel. Okay. The universe has determined that sodium channels must inactivate before they go back to rest. You cannot go from rest to activated and back. You cannot skip this third step. Okay. It's required.